worry about the reality of the universe a bit later. You go mad thinking about stuff like that.
All right, well, welcome everyone to another super happy fun time with Musa and friends for discrete math. Aaron will say words. Would you demonstrate?
Words.
Just to make sure I'm not speaking to the void. So there should be like 100 more students here. So maybe let's just spend a minute talking about some random stuff until the rest of the class decides to show up. And if not, it'll be recorded and posted on YouTube somewhere. So just we were talking before the recording, and you can get paid to write some proofs. So in this class, we're doing CalcCheck, and CalcCheck is primarily functional, but there's a bunch of languages that let you do stuff. This one is specifically for C, right? You write some C code and you throw some stuff in there, and it tries to write the proof for you. So this one tries to find the proof, right? Likewise, Calc, you just say, hey, please try induction, please try this, and it will try to find the proof for you. It's pretty neat. Agda is very popular at McMaster. So if you're like, hey, I want to get a summer job at Mac, Agda might be something you want to learn. And you know how we have that cheat sheet for our class? I also made a cheat sheet for this one and this one. So if you want to get a part-time job for Agda, for CalcCheck, yeah, there might be a part-time job. People have been hired to work on CalcCheck before. So just to let you know, these are things that are out there for you, right? If you Google the word proof engineer, you can find some places that hire for this one. I think the office is called Data 61, and they hire for people programming in Isabelle, which is like CalcCheck, right? So just some fun stuff, just letting you know. Something you can put on your resume. I know CalcCheck, formal methods, right? It's similar to some of these other languages that other people are aware of. Something to know about. You're comfortable with the the Z ISO standard, right? These useful things, practical things you can put on your resume. I know this, I know that. Give me a job, give me a cookie. Nice fun time stuff. So we'll continue with the same train of thought as yesterday. We'll move forward into combinatorics. We'll head on that way, but we'll also keep going back and talking about relations. So just to make sure people are happy with stuff, they're comfortable. So let's start off really quickly, just like yesterday. Let's look at this middle graph right here. Who knows what the image of 3 is? Does anybody know what the image of 3 is under this relation? It's okay, I'll wait. So the image of a relation is all the targets of the nodes, right? So the image of 3. So 0 goes to 3 and 1 goes to 0. And when I ask for the image of 3, I'm saying, where does 3 go? So who knows what the image of 3 is in this graph? Yeah, good. Please continue asking questions. So who knows what the image of 3 is? Exactly. 3 goes to itself and it goes to 1. So the image of 3 is 2 points. What's the image of 2? All right. The image of 2 is all the places that it goes to. It doesn't go anywhere, so the image of 2 is 0. Okay. Sorry, the image of 2 is the empty set. Null, empty. Okay. Good. All right. What about right here? What's the image of 1 in this graph? Where does 1 go in this graph? One in this graph goes to itself, it goes to 3, and it goes to 2, and it goes to 0. So 1 goes to a lot of points. It goes to every point except 4 in this graph. Okay, so Chishu was right. It's 1 goes to 0, 1, 2, and 3. Okay, now the question is, Does it go to 3 once or twice? All right, exactly, Aaron. What does that mean? Does it go to 3 twice or once? And so this is today's topic. We're talking about bags or sets. So let's quickly have a quick reminder of what this is. All right. So a sequence, right? You write it like this: x0, x1, xn, right? Order and multiplicity matter, okay? But then, if you decide to have a set, you write it like this. You say x0, x1, xn, and here neither order nor multiplicity matter. And then finally, today's topic, among others, is bags. So the book writes them like this, ladum, all right? x0, x1. But we also write them like this, x sub 0. Okay. So the two very popular notations, right? Order doesn't matter, but multiplicity does. So sometimes you don't care about the order, but you care how many times something shows up. Okay? Yes, Rishvi. It's good to know these things exist, right? You know, it's good to know that when you see these brackets, you're like, wait a minute. They actually do matter. Square brackets means I can't change the order, and how many times I see a thing, it matters. Sets, I can change the order willy-nilly, and if I see 3 10 times, that's like seeing 3 one time. A bag, however, a bag is like, you can change the order. You know, you have like a backpack and you throw stuff in there, but if you have 2 orange balls in there, then you actually have 2. It actually matters in a bag. You know, you can shuffle them around, but how many times they show up actually matters. So relations in particular, when there's multiple arrows, we think of it as a set, and it doesn't matter that there's 2 arrows. 2 arrows, 1 arrow, doesn't really matter. But for a bag, it does matter, right? Imagine 1 is Hamilton, 3 is Toronto, and then each edge is a road, a highway. Then in a set, we're saying from Hamilton to Toronto, there is only 1 road, and that's enough. There is a road. There is a way. It exists. It is possible, okay? But in a bag, we say, wait a minute. It's possible? How many ways are there? Which ones, right? So a bag says there's this one and that one. There are 2 roads. So sets are about it exists. Existence is enough. I just need to know if I can do it or not, all right? Sets are really just existence is enough. Bags, right? I need to know which one, right? I need to know, right? So that's the slight difference. How many, which one? I need to be able to identify. It's not enough to know something exists, okay? And this idea of existence will get us to the pigeonhole principle later today. So, for example, Hamilton has, Toronto has more than 1 million people, okay? But the average human head contains less than 500,000 hairs, okay? So there's more than 1 million people, and each person can have about 500,000 hairs on their head. So there's going to be at least 2 people that have the same number of hairs, right? And this common sense idea is called the pigeonhole principle, and we'll come back to it today. So I hope you enjoyed this little silly intro for the lecture, and let's get to the lecture, okay? One of the things that's important right now is with the way things are going, sometimes you might encounter the word with, right? As we've been using it to discharge provisos for theorem statements. But sometimes CalcCheck won't be able to tell why it works. And so you have to use explicit substitutions. You have to actually tell it, hey, I want to use this theorem with this particular substitution, please. Right? And then I'll give it the assumptions. So before, you could just say, I'm using this theorem, and then you give it the provisos that discharge it. But sometimes you need to actually say, hey, these substitutions, please. Otherwise, CalcCheck might not be able to tell. Okay, so just something to let you know about. Isabel, for example, also does stuff like this, where you can explicitly make things clear. So do the other languages, right? So there's a difference between inference, where the system can figure out what things should be, versus where you explicitly tell the system, hey, you're not going to figure this out, you dummy. Here, let me tell you. Okay, just want to point that out in case some of you run into this issue. All right. So yesterday we talked about these. So let's spend a moment and talk about transitivity for randomly out of a hat. So let's look at this graph. Can anyone find an instance of transitivity? Is there a triangle somewhere? Right. So transitivity means there's a triangle, right? So for example, I can go from 2 to 4, that's one edge, and then from 4 to 1, and then I complete the triangle by going from 2 to 1. Okay, there's triangles, right? So transitivity means there's always triangles everywhere. My graph is composed of triangles. Any two-step path, one step, two-step, can be shortened to a single-step path, and so I have a triangle. Okay. You can also do 2, 4, 1. That's right. What else could you do? Can you do any more? I think that's it. That's all you can do here. What about right here? Can anyone find an instance of transitivity? So the graph itself is not transitive, because if I do 3 and then down here, there's no way to go from 3 to 1. So the graph is not transitive. What about this graph? Can anyone find an instance of transitivity? 5, 4, 3, 2, 1. So a lot of people said 4, 1, 3. I go from 4 down to 1, down to 3, and there's the outside, right? So wherever you see a triangle, that's a clue. So 4 goes to 1 goes to 0. Here's a triangle. I can go 1 to 0 to 3, and then I can go 1 to 3. So whenever you see a bunch of triangles, you're like, wait a minute. So if your graph is all triangles everywhere, it's transitive. Okay, ducks. Alrighty then. Let's move on. Okay. We talked yesterday about how it can be quite difficult to prove properties when you decide to expand the formulae out. Okay. So here's the formulae. They're just monstrous. Right. They get longer and longer. Look at this. Longer and longer and longer. Right. So it can be really difficult to expand them out all the time. 2, assignment 3, and assignment 4, you didn't have the option of expanding them out. We just told you, hey, there's an operation called fat semicolon, deal with it, right? We said it's a placeholder for like multiplication or conjunction or some other operation. We told you it was a placeholder, and now we're telling you, here's a particular way to interpret the placeholder. You know, Aaron is always saying, Musa, what does it mean? What does it mean when you say R times R, right? What does it mean when you write this? I just tell him it means R times R equals R. And he's like, but what does that mean? And then if I give him an interpretation that semicolon means relation composition, that is, it means travel one edge and then travel another edge, okay? And then he's like, oh, okay. What this means is that if I have a 2-step path, I can reduce it to a 1-step path, okay? That's what it means if we're talking about graphs, okay? But what does it mean if we're talking about matrices or if we're talking about programs, right? So now he's like, so depending on your interpretation, symbols can have a life of their own. So just something to remind you about. So we looked at some examples. Does anyone know why this one we have right here? This is transitive. Does anyone know why this is transitive? Yes, Aaron, what does that mean? So transitive means, again, any 2-step path can be reduced to a 1-step path. So there's no two-step path. Clearly, we're done. What about here? There's no two-step path at all. Okay, we're done. So this is transitive. This is transitive. This one, here's a two-step path, but there's no arrow from C to Q. So this is not transitive. There's no triangle, right? So even if two things are transitive, when you mix them together, you lose the ability, right? So if you have more than one arrow between any two things, there has to be a triangle. Here we only have one arrow, and we don't have a triangle. All right. Okay, ducks. So here is another theorem, which was implicitly hidden in the midterm, right? And which we proved way back when by making use of the fact that self-inverse is converse. And if you really are, you're like, I want to be able to practice my quantifiers. I want to write all those for alls. All those exist. I want to breathe life to them. Okay, fine. Replace this equals with a for all exists and try to write this out. It's pretty ugly. Like it's just a bit ugly. There's essentially no information gained by doing it. But just to let you know, you can practice doing it that way. But I would recommend to just do it this way. It will save you a lot of time, especially on exams and things. Okay. Yeah, exactly, Mohammed. Converse is involutive. All right. I'm pretty sure is that not the word I used? I thought that's the word we used. Yes, right here. Converse is involutive, right? When an operation undoes itself, it's called an involution, right? So that's what that is. Okay. Ready then? Let's go back here. Okay. So this is where we left off yesterday, right? Domain range restriction. So let's get some new graphs. These graphs are getting boring. Let's get some new graphs up there. All right. So the first one says domain restriction, and it says if you have a relation R, okay, and you might have seen these arrows before for cons and snock. So we're overloading the notation, okay? So if you have a relation R and you have a set A, then we're going to form a new relation. It's going to be the same as the relation as before, but now here's the intersection part. We keep only the start edges that are, the nodes that start in A, and don't care. The other ones can stay where they are. Okay, so it's just R, but the starting nodes must be inside A. All right. So here's a complicated graph. It looks mighty scary. What's the domain restriction of this graph for 0 and 2? Suppose I restrict this graph to the domain 0, 2. What's the result? What do I have left? All right. So when I restrict this graph to just 0 and 2, that means I throw away all the edges that are not coming out of 0 and 2. So let me do this one. So this edge goes away, this edge goes away, that edge goes away, this edge goes away, this one stays, this one stays, this one stays, and that one stays. So I have this new graph, which has 0, 1, 2, 3, 4, but only these edges stay. This one, check mark, check mark, check mark, and that one. Okay, so those are the only ones that stay. So it's the edges that stay. Okay, so we still have all of the nodes. All the nodes stay here though. We have all the nodes. Okay, so we have this one, we have this one, we have this one, and we have this one, and we have this one. So all the nodes stay, but we throw away some edges. We just say, throw those one out. We don't care about those. Excellent observation, Tammy. Good job. So let's do another one. So let's just move to another one. This time, domain anti-restriction says, I want to keep everything that is not touching A. So let's look at the same graph as before. And this time, let's anti-restrict 0 and 2. So what's going to stay if we throw away if we anti-restrict with respect to 0 and 2? Who knows? Okay. So we're going to keep everything that's in the relation, and then we're going to keep all the target nodes, but nodes only the ones not in A. So for 0, 2, who knows? We're going to throw away 0 and 2. All right. So I keep everything that's not touching 0 and 2. So let me change color, make it a change color. Okay. So we get rid of this. Oh, no, wrong diagram. We get rid of this one. This one's bad. That one's bad. That one's bad. And this one's bad. And then we keep the rest of the whole graph. Okay. So we just throw away these three. Okay. Does that make it clear? Yeah. Alrighty. And then likewise, we can restrict the targets or anti-restrict the targets. All right. So I talked about image at the very beginning. So let's get back to that in a moment. All right. When you talk about the image, you're saying I want to look at the target nodes. All right. So when I want to look at the image of R, oh, wrong diagram. This one. Okay. So let's go back here. Let's look at this new one, actually. This one's interesting. What's the images of 0 and 2 in this graph? All right. Vote now. Vote fast. Vote hard. What's the images of 0 and 2 in this graph? Remember, the image is where all the target nodes are. Okay. So the images of 0 and 2 are all the nodes that 0 and 2 point to. Okay. So the images of 0 and 2 are really just 2. Very, very boring, because 0 goes to 2 and 2 goes to 2. All right. Let's try something more interesting. What is the image of 3 in this graph? What is the image of 3 and 4 in this graph? What are the images of 3 and 4 in this graph? Vote now. Vote fast. All right, so please keep guessing. I'll count 5, 4, 3, 2, 1. So the image is the collection of nodes that we're pointing to. So the images of 3 and 4 are all the nodes that 3 and 4 point to. So 3 points to itself and to 1. So 3 and 1 are in there. And 4 points to 3, and that's it. So there's 3 and 1. That's the image right here. All right. Everyone got that. That's fantastic. Okay. So when we're trying to compute the image, we're saying, hey, I want the relation, right? And I want to restrict my domain to just A. So I want only the points that live in A. So I was talking about 3 and 4. So I only want to keep the arrows that start at 3 and 4. Okay. So what does that mean? That means I only keep the arrows that start at 3 and 4. So I keep this one. Let me put the timer back on. I keep this one, and this one. Okay, and then I throw away the rest. Okay, so the rest are all gone, and then I say, let me get the range of the resulting subgraph. But the range is just the targets of all the arrows. So this guy's clearly a target. That's great. So he's in here of this one. This one is not in here. There's no check mark by this arrow, so it's not in the subgraph. This arrow is in here, and 3 is a target. And so there you go. I have 2 targets, and that's it. And so we can define the image as the range of the domain restriction. All right. So image is a very handy concept, and then to talk about image, we had to talk about a range restriction. So that was pretty cool. All right. Alrighty then. So I'll leave that alone, and there's more things to address there. And I hope you'll read these examples since the slides are posted online. But I'll continue to show you some more silly stuff with graphs as we talk about them. Okay. So The next interesting kind of relation you'll see is called equivalence. Sometimes you'll see it like this. Do you see this curly guy? Right. So this one or that one. Sometimes people will use this one. Right. So these are notations for equivalence symbols. Right. And the idea behind equivalence is it models notions of similarity. Okay, so what does it mean to be similar to another thing? When are two things the same? Well, that's a dumb question. If I have two things, they can't be the same. I just said I have two. I have two things. They can't be the same, right? But maybe they're similar enough that I don't want to distinguish between them, that I want to treat them as if they were the same for my practical purposes. Like the number 1 and the number 0.9999999 forever, going forever and never stopping. They're definitely not the same, right? Like, but I want to treat them the same when I'm doing math, right? So 1 is really 0.9999999. Show you 89. So that's way more nines than I wanted to put in. That's too many nines. My system's going to crash. That's hashtag sad. All right, maybe I can stop. So that's let's just ignore that. I put in way too many nines. Seg fault, yes, unfortunately. So let's see if that comes back to life. But another thing you want to say is when two things are the same. For example, 2 plus 2 and 4. Those are clearly not the same. 2 plus 2 is three things. 2 plus 2. And 4 is one thing. So 2 plus 2 and 4, like 2 plus 2 is 3 symbols and 4 is 1 symbol. They are clearly not the same. They're not the same. But they evaluate to the same thing. They reduce, they simplify to the same thing. So when I say 2 plus 2 equals 4, what I'm really saying is their evaluations are the same, right? So when we talk about equivalence relations, we're saying they're clearly not equal, but they're so similar that I want to say they're equivalent or indistinguishable or similar, okay? And so that's what we're going to do. Nope, that's not coming back to life. Let's just force quit that. Just did to me. Force quit. Okay. Let me open up another instance in case we want to look at more graphs and things. So that's what equivalence relations are. Now, what does it mean to be similar? Well, everything should be similar to itself. That's what the first one says. Oh, let me change my drawing tool. Go here. Okay, so everything should be similar to itself. So that's what the first one says, right? Reflexive, everything is similar to itself. If B is similar to C, then C should be similar to B, okay? If B and C are similar and C is similar to D, then B and D should be similar, okay? So these are the properties of similarity that we expect as people. So even if things are not equal, if they're similar, that is, and we have a relationship that has all these properties, then that's usually good enough. Okay, so that's what an equivalence relation is, and you'll see equivalence relations out of the wazoo. Like, what does it mean for two programs to be the same? If I have a program that loops for 1,000 steps and then prints hello, and I have another program that prints hello, they're clearly different programs. They are massively different. One of them will take a while before it prints, and then the other one will print right away. But they're equivalent in that they produce the same behavior. Right, so equivalence relations are are everywhere in computer science and in math. So it's important to be aware of this idea. So what we're talking about it now. You will definitely see equivalence relations like next term, for example, automata in math and in programming. They're just everywhere. Okay, a very common notation is if you have a relation xi. And this relation xi is an equivalence. What some people do is they write square brackets, subscript xi, to mean this is all the things that are equivalent to B. All right, that is, x is equivalent to B. Okay, so this is called the equivalence class of B. Right, so another popular term you'll see running. All right. So yesterday we talked about what is the number 3. What does the number 3 mean? Well, numbers, this is what people do. Numbers are defined as equivalence classes. So the size relation. So you say two sets are related or equivalent if they have the same size. Remember yesterday we said isomorphic sets have the same size? Well, if you say, hey, given any two sets, they're equivalent if they have the same size. And when you consider the equivalence classes, those are called numbers, right? So the finite equivalence classes are called numbers, right? So if you start off with collections, and then you consider equivalence modulo size, then the equivalence classes are called numbers. Yeah, life is weird. To really know what a number is, you have to first learn about sets, and then learn about equivalence relations, then learn about equivalence classes, and then say, oh, a number is just an equivalence class modulo size. And yeah, it's isn't math fun? I don't know. It's neat stuff, I think. I think it's neat. Okay. And incidentally, an equivalence is sometimes also referred to as a partition, because if you have a bunch of stuff in your space, so like right here, notice it gets split up into chunks or cliques, right? There's a first bunch here, then another bunch right here, and then a third bunch, okay? So all of these equivalence classes actually like separate your space into distinct pieces, distinct disjoint pieces, and they split it up, they partition it. So an equivalence relation and a partition are the same thing, okay? For more details, you can look in the book, but that's a pretty cool thing, I think. All right. Maybe let's bring this guy back. All right. Boop, boop, boop. It's maybe time to look at another graph. All right. So we talked about bags earlier. So let's get back to bags, and maybe I can show you a graph. Do I have a graph available anywhere? Let's see. Where did my graphs file go? Oop. Is it here? I have too much sensitive information. Cannot show you everything, unfortunately. There you go. Okay. But that's because I'm a messy guy, apparently. All right. So let's so recall when we talked about graphs. Boop. Boop. So not here. This one. Okay. Symbols function definition is void. Oh. There you go. Gotta load all that code again. Let's get rid of all this markdown stuff that really shouldn't be here. Okay, so here's some. Let's get some new graphs up in here, because these ones are lame and boring and stale, and we need some new exciting stuff. Look at all these zany lines over here. Oh, scary. So here's notice right here, from 0 to 4 we have one edge. From 0 to 2, we have one edge. But over here, we have 3 goes to 1, and 1 goes to 3. Still no parallel edges. I thought I had some parallel edges here. Let me, let's try to get some parallel edges in here. Okay, so recall that a bag allows you to have multiple things, all right? So here is an example where from 0 to 4, I have 2 arrows coming. Okay, so a relation, almost always people think of a relation set-wise, right? You think of it as a simple graph, and you know what? The number of arrows going between things doesn't matter. As long as it exists, that's enough. I just need to know there is an arrow. I don't care how many, right? But when you think of relations for graphs, they're called multi-relations. Multi-relations means I care about the multiple edges. Right. So this is a relation. This is a relation. This is a multi-relation if you care about the multiplicity of the edges. So I hope that helps. The notation and the way you treat them is essentially the same, but notice here, multiplicity doesn't matter. Having 3 zeros and 1 zero is fine, but for bags, multiplicity does matter. That's why a bag is sometimes called a multi-relation, to emphasize. Bags are also sometimes called multi-sets. Okay, so let's so called multi-relations or multi-sets. So some places, especially in particular in math, you'll see these called multi sets. Okay, so that's what some people do. They'll say, hey, this is a set with multiplicity, like to emphasize the importance of it. But the name bag is also nice because it just says, hey, these are atomic things. They're not built on top of sets. They're just an atomic thing by themselves. Right? So for example, this hashtag operation counts how many times an element appears in a bag. So remember, we had a membership, right? Right. So membership is the key thing here, right? Key thing, right? Right. I just need to know if things exist. Whereas here, hashtag is the key, right? How many times is it there, right? So if it's in the bag 0 times, that's like not being in the bag at all, right? It's not in there. If it's in the bag more than 0 times, then that's like it's being in there, but I actually care about the number. So here's my bag. It has 3 zeros, 2 ones, and 1 4. And I'm saying, how many times is the number 1 in here? And the number 1 is in here 2 times. Okay, and all the operations you've seen for sets also apply to bags. 2 bags are the same when every element is in the bag the same number of times. Okay, 1 bag is included in the other precisely when the bigger bag has the element at least as much as a smaller bag. Right? To union 2 bags, you add up the elements because the order matters. It's not or, right? So remember, before union went to the operation or. It's not or anymore because we actually care about the number of times it shows up. And or is idempotent. P or P, just P. But here, 6 and 6, well, that's 12, and that matters. Intersection says, find out how many times it occurs here and how many times it occurs here. And I just want to get the commonality. So I want the smallest number, right? Smallest number is minimum, right? So this is a nice way to look at these things. And notice before union and intersection went to or and, now union and intersection go to plus and minimum. When you work with math with plus and min, you're doing tropical mathematics. So fun names, tropical math, when you're working with plus and max or plus and min. Alrighty? Sometimes you just want to know if something's in the bag and don't care about the number. And so you have this boxed membership, right? And we say X is in here means the number of times X is in B is not 0. Okay? So this is just a Boolean. So the difference is hashtag returns a number, box epsilon returns true or false. Okay? A number is way more informative than just true or false. Okay? Right. And just as before, you can do quantification over these things, right? If you multiply every element here, you'll get 2 times 2 times 3 times 3 times 5, 180. All right, so just some stuff to share. So now that we have bags, right, and bags are multi-relations or multi-sets, we can go back to that thing I said at the very beginning. The number of people in Toronto, you can always find at least 2 people that have the same number of hairs, right? Now this exists. I can't tell you who those people are, but there are at least 2 people in Toronto that have the same number of hair. So that sounds like a ridiculous claim, or obvious, depending on who you ask. Okay, so here's a fun. Hopefully, only fun things. Okay, bald people have the same. Yeah, there you go. If there's 2 bald people, then you're good to go. But maybe there are no bald people. So let's do a little puzzle. Suppose there's 8 friends in a room, and these 8 friends are trying to find out what their birthdays are. Then I can guarantee you 2 of those people have the same birthday day of the week, right? because there's 8 people and there's only 7 days of the week. That means each person can have the first 7 people, they might all have a different birthday of the week, but then all the days of the week are used up. And then the eighth person has to land on one of those days as well. And whatever day they land on, now I have 2 people sharing the same birth date. Okay, and the idea for the number of hairs for people in Toronto is the same thing. There's way more people than the possible amount of hairs any person can have. And so there's going to be at least 2 people sharing the same number of hairs. Okay, this idea of common sense is packaged up as the pigeonhole principle, right? If you have a lot of pigeons, but not a lot of holes, and you stuff your pigeons in holes because you got issues, then some hole will have more pigeons. I will have at least 2 pigeons, right? If I have a bunch of boxes at home and I have 5 boxes, but I have 30 things, then at least 1 box is going to have more than 1 thing. Okay, I have too many things and not enough boxes, so some box is going to have more than 1 thing. This is called the pigeonhole principle. Sometimes it's called the drawer principle when people, are afraid of PETA, right? So math. Yeah, poor pigeons. Bald people do exist. I don't know who said they don't. This is just a toupee. This is fake hair. Okay. Alrighty then. Or they don't want to use animals. So in the book, the idea of using pigeons and holes is it's a nice way to explain things, but to actually use this in calculations is really, really hard. It's not a formula, right? If you have more pigeons than holes, some hole will have more than 1 pigeon. That's not a formula. That's like, what? All right, so we're saying for every bag, there exists at least 1 hole, such that there's a mapping. It's a bit convoluted. And so the way the book decides to present it is to say, hey, if you consider the average of all the holes, right? So count up all the holes and see how many, on average, how much pigeons are in each hole. Then I guarantee you, on average, we'll have less than the maximum number of pigeons in any hole. Okay, and this sounds really intuitive. The average should be less than or equal to the max, and this is a nice, simple inequality, right? It's a nice inclusion. The average of a bunch of numbers is less than or equal to their maximum. That sounds pretty useful, right? So it's nice to explain pigeonhole using pigeons, but to actually work with it, we use this inclusion. Okay. Yes, I agree. Pigeons should not be hole shaped. Good catch, Eamon. So here's an example. We were talking about people having the same birthdays of the week. This is from the book, and to find out that there is at least 2 people with the same birthday, we say, all right, let S be all the days of the week, and I'm trying to find out the maximum number of people that have the same birth date. So the maximum number of people with the same birth date. By the pigeonhole principle, I know the maximum is going to be at least the average. Okay. Well, there's 8 people and 7 days, so 8 divided by 7, right? That's 1 point something. But I'm talking about whole numbers, so I round up and I get 2. Okay. And so that's where if you have 8 people in a room of 7, then at least, right? At least one of those days will have 2, right? There you go. Which one? The one that's the maximum. There you go. The day with the maximum number of occupants is the one that has at least 2 people. There you go. I told you which one. The one that has maximum number, or any one of them that has a maximum number. Right? So this is a nice way to actually use the pigeonhole principle. All right. All right. So I like that today we've been able to go everywhere. We started with beautiful graphs. I hope you like my art. I work really hard at it. It's my craft. I make a living off of this art. Then we realized, whoa, I draw multiple arrows. These things are called multi-relations. A relation is a set, a multi-relation is a bag. Then we're like, all right, we need to talk about this multiplicity, and we need to talk about images. And so that led us to domain restriction, domain anti-restriction, and then we got the images. And then we're like, wait a minute, how do we actually deal with these bags? What can we do with them? And we're like, oh, this can lead us to the pigeonhole principle. And now that we're done with that, let's go back to graphs and talk about symmetric closure one more time. So if you remember from the this little cheat sheet, the symmetric closure is when you forget about the directedness of the arrows. Okay, so let's do a simple one together. What do I have to do to this one to make it symmetric? Right. So symmetric means throw in all the pieces needed to have arrows going between any two nodes that are already related. So what do I have to do to this graph to make it symmetric? I have to put an arrow from 2 to 1. Yeah, that's exactly it. Good job, because there's no other arrows. What about this one? How do I make this one symmetric? How do we make this one symmetric? I have to add an arrow this way. Oh, that arrow's gone. I have to add an arrow this way. I have to add an arrow this way. I have to add an arrow this way, and I have to add an arrow that way. Okay, so I have to add 4 new arrows. Okay, and that's exactly what's going on right here. It says look at the existing relation and then add all the other ones in the other direction. Okie dokes. All right, I like that people are Rishi. Yes, you add lots of arrows, but you need to try. So good job, Nathaniel and Tammy. All right. Okay. Now let's move to the interesting question. This graph right here is clearly not transitive. Transitive means any 2-step path can be reduced to a 1-step path. That is, you have triangles. I have a path from 0 to 2 and from 2 to 3, but I have no path from 0 to 3, right? I should have a path this way. So this graph is not transitive. What arrows do I have to put in to make it transitive? All right, so let's try doing that. Okay, so to make it transitive, all right, we have to fill in, we have to complete the triangles, right? So here's one edge, here's one edge. This should be a triangle. Okay, good. Is there any others? Here's one, here's one. This should be a triangle. So there you go. Okay, good. What else? Are there any more triangles? I can go from 1 to 2 to 3. So there should be a path from 1 to 3. So it doesn't look like a triangle, but I need to draw one like this. La 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 la, like that. Okay. And are there any more? I can go from 4 to 2 to 3, directly triangle, 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 and there you go. So now my graph is reflexive. All right. And that's it. Okay. There are no more. It's transitive. It's transitive. It's a transitive graph. Any 2-step path can be reduced to a 1-step path. All right. Now, this is the topic of the next thing. So symmetric means we want to make it like that. Reflexive means add in all the loops, right? So all the loops should be added in right here. And then transitive and reflexive says, let's add in all the loops and add in all these 2-step paths right over here. Okay. So we're running out of time. So maybe we'll pick up here tomorrow. I hope you've enjoyed today. I hope you have a fantastic Friday. I like that you're all participating. So maybe we'll continue doing graphs just for funsies along the side. Please remember to do the course evaluation. Then maybe I'll get hired next term and I can teach you again. You know, all those hearts and likes and shares will get me a job. Yeah, I hope you're learning, and I wish you all a great weekend. I'll be here to answer questions if you have any. And everyone else, all the best. And let's stop recording. Boop.